Right. Hello, doctors. Good morning, all. How are you? Well, I hope you are doing well, right? Okay, good, guys. Okay, be healthy. Okay, be healthy and prepare well. Okay. Okay, guys. Okay, today we are going to discuss about the some more very hard topic in organic chemistry for this competitive exam. Okay, for every competitive exam, whether it may be NEET, JEE, JEE, etc., 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 anything it can be. Okay, for every competitive exam. Okay, these are also very important reactions. Okay, let me those reactions from the basic level to application level. Okay, now right. Okay, let us go through that, guys. Okay. Okay. So the first reaction, today's first reaction, very hot topic is about a Wurtz reaction. Okay, very important. Okay, doctors, what is a Wurtz reaction? So Wurtz reaction is okay. So the reaction of halides, alkyl halides with the ether like PHF. Okay, triether like PHF. Okay, what happens here? See here 2 moles. Okay, 2 moles of alkyl involved in the reaction and results in the formation of the respective higher alkane. Okay, this is called as higher alkane. It is giving respect to higher alkane. Okay, now right. So here see what are the reactants? Reactants are the alkyl halides. Okay, reactants are alkyl halides. And the products here, products are the higher alkanes. Higher means so the product will contain some more number of carbon atoms than reactant molecule. Okay, then the product is called as a higher product. Since the product is a alkane, this is called as a higher alkane. Okay, right. And then what is the byproduct here? The byproduct is a okay, this is generally called as a Wurtz reaction. Let me tell you some important things about this Wurtz reaction. Okay, so generally, guys, here this Wurtz reaction is two types. Okay, this Wurtz reaction is 2 types. So what are the 2 types of Wurtz reactions? Let me tell you that. So in this Wurtz reaction, 2 moles of same alkyl halide is involving. Correct now? So 2 moles of same alkyl halide is involved in this reaction, resulting in the formation of the respective alkane. Okay, such kind of Wurtz reaction is called as a Wurtz reaction. Okay, this is called as a simple Wurtz reaction. So simple Wurtz reaction means so whatever the alkyl halides involved in the reaction, both alkyl halides are the same kind. Okay, then only it is called a simple Wurtz reaction. Okay, right. Next, let me give you the another Wurtz reaction. Okay, suppose guys take one alkyl halide RX. Okay, right, and react it with the sodium. Okay, here also 2 moles of the sodium involved in the reaction. Another alkyl halide, here different alkyl halide we are writing. So here R and R prime both are the different, not same. So this is one alkyl halide, this is another alkyl halide. Suppose if it is this is an ethyl halide like that. Okay, so then here you see the loss of sodium halide and a carbon-carbon new bond is forming between them. Okay, 2 carbon atoms of alkyl groups and resulting in the formation of this alkane. See, okay, this is also higher alkane, but so this higher alkane is from the 2 different kind of alkyl halides. R is not equal to R prime. So 2 different alkyl halides and giving the respective higher alkane. Kind of mixed or crossed Wurtz reaction. Okay, mixed or crossed Wurtz reaction. Okay, na? Easy na? So take a screenshot of these 2 reactions. So Wurtz reaction is a 2 types based on the kind of alkyl halides involving in the reaction. So if the Wurtz reaction is taking place between the 2 moles of the same alkyl halides, that is called as a simple Wurtz reaction. The reaction is taking place between the 2 different kind of alkyl halides. Then important things about the simple and cross Wurtz reaction. Okay, so please take a screenshot of this case. Okay, well, things about this Wurtz reaction for exams, for competitive exams. Okay, let us go to that. So Wood's reaction is how many types? Two types. Okay, two types. Okay, see. Wood's reaction is two types. Okay, so number one. Okay, simple Wood's reaction, and number two, mixed. In some books they are mentioned as a crossed. Both are same. Okay, crossed Wood's reaction. Remember, in these two reactions, it is impossible to prepare the methane. Okay, the first important thing. So methane CH4. Okay, CH4 cannot be prepared by Wood's reaction. Okay, in simple and in cross Wood's reaction, it is impossible to prepare the methane. Why? Because here we are getting the higher alkane. So what is the alkyl halide with the minimum number of carbons? That is methyl halide. So the higher alkane will contain some more than one carbon atom. So it is impossible to prepare. The methane by this reaction. And the next, okay, the simple Wood's reaction is here now. Simple Wood's reaction. So in simple Wood's reaction, okay, we will get symmetrical. Okay, symmetrical higher alkanes. Okay, symmetrical alkanes. Okay, now important thing. And whereas in the mixed Wood's reaction is there now. Okay, mixed Wood's reaction. Here in this reaction, so we will get mixture of products. Okay, mixture of products we will get. How many products we will get? Suppose if the two different alkyl halides are there, then we will get the three products. Okay, that is three products we will get. If the Wood's reaction is taking place, but in the two different reactants, here we will get the three products. Okay, right. So here it is giving the single product. Okay. And here we are getting the mixture of the products. Okay, and here we are getting the symmetrical alkane. I will tell you what is symmetrical alkane. And here we may get both symmetrical, symmetrical and unsymmetrical higher alkanes. Both we will get here. Symmetrical and unsymmetrical higher alkanes we will get. Okay. Put it up. Okay, understood guys? So please, take a screenshot of these things. Okay, let me tell you that. Okay, let us go to the simple examples here. So darkness here, we need not to discuss about the mechanism. Okay, here mechanism, we have the two types of the mechanisms. One is ionic mechanism is here, another one is a radical mechanism is there. Okay, so let's see that. Okay, well guys, mechanism is not that much of important here. Okay, because we are doing the quick revision. Knowing the mechanism is good. Okay, but here we don't have that much of time. So that's why guys we are not discussing about the mechanisms here. If it is necessary, I will tell you that. Okay, well, let me tell you. Okay, one reaction. Okay, some examples with the simple and mixed Wood's reactions here. Suppose guys, if you take CH3CH2Cl. Okay, right. Well, so reacted with the sodium in dry THF. Okay, right. Well guys, here see, in the reaction they will give like this only. They won't mention the 2 moles of the ethyl chloride is involved in the reaction. They won't mention. We should understand that. How to understand? Very simple. So here see, if alkyl halide is here, if the sodium metal is here in dry ether, no doubt it will be the Wood's reaction. That's all. Okay, like that you have to understand. Okay, well, so this is a Wood's reaction. Okay, we know as we have the very good knowledge in chemistry, we will come to know that immediately. So 2 moles of alkyl halide involved in the Wood's reaction. Okay, so then what happens here? Very simple now. So break the bond here. How to write the product? Okay, just break the bond here between the carbon and the chlorine and write the group as such there. Okay, however it is, you can just write the same group here and write the same another group. It's mirror image. Okay, so you can write it as CH2CH3 and between these 2 carbons, make a new bond. That's how you will get the product. Okay, now? So what is the advantage? What is the application of this reaction? This is a reaction used to make a carbon-carbon single bond. Okay, this in this reaction, what is happening? New carbon-carbon bond is forming here. Important to observe this. Okay, now right. Okay, let me tell you one more important thing. Why should we use a dry ether? Why should we use a dry ether? What happens if it is a moisture ether? Very, very important. If moisture ether we are using, in case we are using the moisture ether, so then what happens is the sodium will react with the moisture water to convert into sodium hydroxide, and which cannot generate the radicals. We will get aqueous sodium hydroxide. Okay, causes to the nucleophilic substitution. Causes to nucleophilic substitution. So it will not give the this product. So that is the reason why, to avoid that nucleophilic substitution, okay, we have to use a dry DHF. Dry means without moisture. So if the moisture is there, okay, if moisture is there, the sodium, okay, metal, highly reactive metal, okay, readily react with the water, okay, very highly exothermic reaction, okay, produces aqueous sodium hydroxide, okay, it may cause to the nucleophilic substitution. So to avoid this, okay, so this is nucleophilic substitution to give the alcohol. So to avoid that, okay, we have to use a dry ether. Okay, and sodium is a metal which can generate the radicals easily. Okay, right. So what kind of Urji reaction it is? This is a simple Urji reaction. We are getting the higher alkane. Higher alkane, that is symmetrical. Symmetrical means if you divide it, okay, you will get the two equal halves. Okay, if you divide at the center, you will get the two equal halves. So that is called as a symmetrical alkane. Okay, how many products we are getting? Single product. It is a simple Urji reaction. Okay, now let me give you another example. Okay, suppose you are taking, okay, let us take this molecule, okay, let's take this molecule, okay, that is, okay, chlorocyclohexane, okay, react this molecule with the methyl chloride in sodium in dry DHF, okay. Tell me how many products we will get? We will get a mixture of 3 products. Okay, because so here the reaction is taking place between the two different molecules, different alkyl halides with the sodium and dry ether. So it is a mixed Urji reaction. In the mixed Urji reaction, the two different alkyl halides are participating. We will get a mixture of the 3 products. Okay, well, how to write them? So here see, okay, here see, you are taking the 1 mole of this compound, 1 mole of this compound. 1 mole means Avogadro number of particles will be there. Okay, 6.62 or 6.6 into 10 to the power 7, 6.023 into 10 to the power 23 molecules are there. Very high number of molecules are there. So, okay, the reaction can take place between the 2 moles of cyclohexane, okay, chlorocyclohexane. So it results in the formation of the one product, and the 2 moles of the reaction can be takes place between the 2 moles of the methyl chloride. It gives a ethane, and here you may get this product also. Correct now? And the reaction is takes place between chlorocyclohexane and methyl chloride, and it results in the formation of this product. Okay, so this product, methyl cyclohexane, and these two are the byproducts. Okay, these two are byproducts here. Okay, like this. Okay, we are getting the mixture of the 3 products. So these mixture of the 3 products, okay, may be symmetrical or unsymmetrical. How many symmetrical molecules are there? So this is, and this is. Okay, both of these are the symmetrical molecules, and in mixed Urji reaction, one unsymmetrical molecule will be formed here. One unsymmetrical molecule will be formed. Okay, symmetrical means if you divide into at the center, you will get the 2 equal halves. So therefore, this is symmetrical. If you divide at the center, you are getting the 2 different equal halves, unequal halves. Okay, that is called as an unsymmetrical or asymmetrical or higher alkane. Clear? So please note these examples for the which represents one simple Urji reaction, mixed Urji reaction, number of the products, and what is a symmetrical alkane, what is an unsymmetrical alkane. All these things we can see here. Okay, so please take a screenshot. Okay, right. Well. Now, let me tell you some other important things about this Urji reaction. That is about R of reactivity. Okay, now? Okay, guys. Here, see, if you see the R of reactivity, okay, for a given halogen, okay, R of reactivity. Generally, guys, okay, R of reactivity, okay, is inversely proportional to, okay, steric hindrance. This is a very important thing to remember. Steric hindrance. So that means if the steric hindrance of alkyl halide, okay, it is must. Okay, steric hindrance of Alkyl halide. Okay, alkyl halide. So in alkyl halide, if the bulk groups are present at alpha carbon atom, okay, the reaction is difficult. Okay, and if the small groups are present, okay, steric hindrance is less, so reactivity is more. Okay, this is a basic thing. So based on this, okay, based on this, we can write the order of reactivity. Okay, order of reactivity. Okay, in the different ways. Okay, first case is that for a given halogen, it means halogen will be same and different alkyl groups will be present. So alkyl halides are the how many types? Okay, methyl halide, primary, secondary, tertiary alkyl halides are there. Okay, so in that case, see, okay, methyl halide reactivity is more, okay, towards Wurtz reaction. Okay, then primary alkyl halide reactivity is more than secondary alkyl halides. Okay, secondary alkyl halides, and secondary alkyl halide reactivity is more than tertiary alkyl halide. Okay, tertiary alkyl halide. Here, one important note point I am telling you guys, that is, okay, in case of tertiary alkyl halides, okay, in case of, okay, tertiary alkyl halides, okay, Wurtz reaction is not possible. Okay, Wurtz reaction is not possible. In case of tertiary alkyl halides, elimination takes place. Okay, elimination, okay, takes place here. In which case? In case of the, okay, in case of tertiary alkyl halide. So tertiary alkylides will not participate in the Wurtz reaction. Okay, so they readily, okay, even the same condition, sodium triether, they undergoes a, okay, elimination. Elimination takes place to give alkenes. Elimination means definitely we will get unsaturation. Okay, to give alkenes. Important to know. Okay, I will tell you. Okay, suitable examples here. So this is the order of reactivity for a given halogen. So different alkyl halides are there. Given halogen means halogen is the same and different alkyl groups will be same. Based on the different alkyl groups, we have the different types of alkyl halides. Okay, we can follow this one. Okay, next, let me tell you another case. Okay, for a given alkyl group. Okay, for a given alkyl, that means if the alkyl group is the same, okay, different halogens are there. For a given alkyl group, okay, then how will be the order of reactivity? Okay, for a given alkyl group is the same. So that means and different halogens will be there. So that we can write it as a methyl fluoride. Okay, and methyl chloride, like that. Suppose any alkyl group you may take, but alkyl is the same. It must be the same. Methyl chloride and methyl bromide and methyl iodide. So alkyl is the same, no? Different halogens are there. Then how would be the order of reactivity towards a Wurtz reaction? So that is, okay, so that is depends upon the bond dissociation and Thalffi. Okay, so it is, okay, increases in this way. So methyl chloride to methyl iodide, the reactivity order is a more. Clear na? Understood? Okay, na? Right. So take a screenshot of this. So these are some important things to know about Wurtz reaction. Some more things are there, very important for complex exams. Okay, everyone must know these things. Okay, right. Okay, well guys, let me tell you some other things in the Wurtz reaction. Okay, that is, okay, few important things are there. Okay, right. So in case of the, okay, in case of the monohalides and polyhalides, okay, in case of the monohalides, we can see the two types of reactions. One is a simple Wurtz reaction, another one is a mixed Wurtz reaction. In case of the polyhalides, how will be the reactions? Okay, let me see. Okay, so here let me tell you that. Okay, Wurtz reaction is there. Okay, Wurtz reaction is there. Okay, very important things, guys. Simple things only. Okay, so this is the two types. Okay, this is two types as we discussed. Okay. So here I am dividing based on the number of halogens into two types here. Okay, so monohalides. Monohalides means which contains only one halogen. Okay, and Wurtz reaction in case of the polyhalides. Let's see how it will be in case of the monohalides and in case of the polyhalides. So doctors here see, okay, monohalides and polyhalides. In this case, we have seen the two types. Okay, one is the simple, another one is a simple, another one is a mixed. Okay, simple and mixed, we discussed everything here. Okay, so here simple, in the simple Wurtz reaction and mixed Wurtz reaction, methane cannot be prepared, and in the simple Wurtz reaction, single product will be formed, and the mixed Wurtz reaction, okay, mixture of the products are formed. In the name itself, you can understand that. Okay, no? And in simple Wurtz reaction, only symmetrical higher alkanes are formed here. Both symmetrical and unsymmetrical higher alkanes are formed here. Number of symmetrical are the 1. So number of symmetrical are the 2, and number of unsymmetrical are the 1. Correct? So this is over. This chapter is over, right? The topic is over. Now let's discuss about polyhalides. Polyhalides means which contains more than one halogen. In that case, okay, let's see. Okay, particularly in case of the dihalides. Okay, very important. In dihalides, okay, Okay, the important thing I am telling that. So these dihalides are the 1,2 dihalides. In case of the 1,2 dihalides, okay, 1,2 dihalides. Okay, what happens is here elimination takes place. Okay, elimination. Okay, takes place here to give the alkene. Okay, elimination takes place to give alkene. Very important. Okay, and again this is A first one. And in case of other dihalides, so that may be 1,3, 1,4, 1,5, 1,6, alpha, omega, anything it can be other than 1,2 dihalide. 1,2 dihalide is nothing but vicinal dihalide occurs. Okay, vicinal dihalides. It is nothing but vicinal dihalides. Other than vicinal dihalides, in any other dihalides, okay, other dihalides, what happens is, okay, so that is 1,3 or 1,4, okay, like that. What happens is, so in this case, cyclization will take place. Okay, cyclization to be the cycloalkane. Cyclization is taking place here. Put it there. Understood? समझ में आ रहा है? Right. Well, so these are some important points to know here. Now let me tell you, okay, the few reactions, okay, regarding these important points and everything, okay, let us go to that. Okay, well guys, so please note all this. Okay, Dr. CFC, let me give you some examples. Okay, let us do it. Here, see, suppose, okay, we know that as we discussed okay, earlier, okay, CH3, okay, CH2 taken 3, 2 taken twice, and CH2I, okay, reacted with the sodium, okay, in dry THF. And could you please write the product here? How to write the product? Very simple now. So just break this bond between the carbon and halogen and write this unit as such. This is the only simple, okay, simple Uji reaction because only one, okay, kind of alkyl halide is involved. One kind, but how many moles? 2 moles. Okay, so write this molecule as such. Okay, that is CH3, CH2 taken twice, CH2, and write this another same unit. Okay, the CH3, CH2 taken twice, CH2, and make a new bond between, okay, these two carbon atoms containing halogens. That's how you will get the product here. Okay. Put it up. Easy enough. Symmetrical higher alkyl, right? It is. Okay, well, let me give you some other reactions. Okay, suppose if you take this molecule, okay, take this molecule. What's the name of this molecule? Iodocyclopentane. Okay, so if you react this molecule with the sodium metal in dry THF, okay, what happens is, can you write the product here? Yes, okay, we can write it now. So we will get this product. Okay, if you react the same molecule, with N-butyl iodide in sodium in dry THF. Okay, so here what would the major product here? So major product can be, okay, just remove this iodine and write a bond between these two carbon atoms of alkyl groups. Okay, and here this is cyclopentyl ring. Okay, and here it is found a bond with the butyl. Okay, which butyl? N-butyl. Okay, N-butyl cyclopentane. That's all simple. Okay, so this is major. And byproducts we can write now. What are the byproducts? Okay, this is one of the byproducts. Another one is di-n-butyl. Okay, are converting together to form another product here. Okay, that you can write here. And another one is, okay, cyclopentane with the cyclopentane 2 rings are combining together. Okay, like this we can write total 3 products. Easy now. So these are the monohalides, right? These are the monohalides. Now let us see reaction of the bihalides or dihalides or polyhalides. Anything you can take. Okay, right. Well, guys. Now let's see some important reactions. Okay, so before that, let me tell you one important reaction with the tertiary halide. Okay, tertiary butyl chloride. What happens? What is going to happen here? Tertiary butyl chloride, okay, react with the sodium metal, okay, in dry THF. What is going to happen? So here, see, we are going to get the 2 products. Okay. Okay. See, here this bond will get break homolytically. Okay, this bond also will get homolytically, and here it generates the two radicals and results in the formation of the one alkene CH3 CH3 double bond CH2. Okay, this is isobutylene. Okay, the name of the product is isobutylene. Okay, and two modes involved in this reaction now. In the another mode, okay, whatever the hydrogen radical is here, that hydrogen radical, okay, this hydrogen radical combined with this okay, radical tertiary carbon radical, and it results in the formation of the isobutane. Okay, isobutane. Okay, this also formed isobutane. Okay, and what is the other byproduct? Okay, that is a sodium chloride. Okay, sodium chloride will be formed as another byproduct. Okay, this is what happening with the tertiary alkyl halides. Okay, na? Okay. So next, let me tell you some other reactions. See, doctors, if you take this molecule, okay, CH2, CH2, Cl, Cl. What is this? 1,2-dichloroethane. Okay, if you react with the sodium, so if you react with the sodium in dry ether, okay, dry BHF. Okay, now what happens? Okay, 1,2-dihalide or bisphenol dihalides now. In the bisphenol dihalides, okay, here homolytic cleavage is taking place. Okay, here also homolytic cleavage is taking place. And here radical are generating now. Since the radicals are on the adjacent carbon, they will combine together to be the alkene. So the reaction is taking place like this. Okay, so here one radical electron, here also one radical electron, both will combine together to be the alkene here. So if it is a bisphenol dihalide, it undergoes a beta elimination to be the alkenes. That is important thing. And suppose if you take the alpha omega dihalides, okay, other than bisphenol dihalides, alpha omega, very terminal, okay, alpha omega means a terminal dihalides, okay. So if you take this molecule, suppose if you take 1,3-diiodo-propane, okay, so same reaction, okay, then what happens here? Radicals are generating here, very simple, radicals are generating here and they are forming a bond. So cyclization is taking place. In this cyclization, total 3 carbons are there, so you can write the cyclopropane as a product. Simple, easy, right? That's all easy. So chemistry is very easy, okay. And you may take any other molecule. Okay? Suppose if you take this molecule, so here see, just let me write the bromine, and here also bromine, okay, bromine, and write one methyl group here, C2H5. Could you please write the product? Very simple, so just break a bond here, this bond, okay, this bond. Okay, then what we have to do? So write the radical electrons here. Okay, so for the sake of understanding, okay, you can give the numbering. Okay, 1, 2, 3, 4, 5. So, okay, in between the first and fifth carbon, the bond is forming. So 5-membered cyclic ring we are going to get. Okay, so just write that 5-membered cyclic ring. Got it, na? And give the numbering. For an anywhere you can start 1, 2, 3, 4, 5. And at second carbon, which group is there? Ethyl group is there. Just write it as such. At second carbon, ethyl group, C2H5. That's all. Okay, you are getting this. Okay, na? Put it there. Understood? Okay, so please write it. Okay, next. Let me give you one more example also here. Hope you can write all this. Okay, so this is 1,2-dichlorocyclobutane and this is 1,3-dichlorocyclobutane. Could you please write the products here? Yes. Why not, sir? Right, let us write it. So here see, here this is the 1,2 adjacent bisphenol dihalide. So elimination takes place, it gives a cyclobutene now. It gives cyclobutene. Okay, right. And here, what happens here? It is 1,3, 1, 2, 3, 4. Okay, 1,3, not a bisphenol. 1,3 dihalide. So no doubt it undergoes some, okay, it undergoes cyclization. So here is one radical is generating and here this radical is generating due to okay, radical generation. Okay, so then here it forms a bond and we are getting the bicyclic compound. Okay, easy na? Bicyclo 1,1, okay, bicyclo 1,1,0 and how many carbons are there? 4. Okay, butane. Bicyclo 1,1,0 butane. Okay, right. So next, let me give you another example. Okay, so another example is that, okay, that is you can write it like this. Okay, one important example I'm telling you. Not this one. Okay. Here see, here is a bromine, and here is a bromine. Take care. Right. So what's the product we are going to get? Could you please write? Okay, see what is happening here. This bond and this bond homolytically cleaving, generating a radical here and forms a bicyclic compound. Correct now, right? Okay, well here see what kind of bicyclic compound. What's the name of the bicyclic compound? Okay, suppose if you give the numbering from here 1, 2, 3, 4, 5, 6, 7, 8. So from the first to fifth, so 1, 2, 3, 4, 5, 8. Here this side 5-member cyclic ring. Okay, 5-member cyclic, because here a bond is going to form, so it is a 5-member cyclic, and this side 1, 2, 3, 4, 5. So 2 5-member cyclic rings we are going to get. Okay, you can write it like this. Okay, 2 5-member cyclic rings we are getting. Okay, so this is the product we are getting. So by bicyclo 3 3 0. Okay, 3 3 0. 3 plus 3 6, 6 plus 3 8, octane. Bicyclo 3 3 0 octane. Okay, put it up. Right. So please note all this. And one more case is here. Okay, that case is, suppose Dr. CFC allyl bromides, allyl dibromide. Okay, in this case, what happens here? In this case, what happens when you add the sodium in dry THF? Same as, okay, here see, radicals are generating from here, one radical, and from here also one radical. So this pi bond also undergoes a homolytic cleavage to give the radicals. So now we are getting this product. Okay, so let me write the skeletal structure first, and later we can understand how to write the products here. So here see, here is one radical, here is one radical, radical, radical. So here pi bond, 1,3-butadiene, alpha beta unsaturated carbonyl compounds we are getting here. Okay, now clear now? So please note all these guys. Okay, well guys, so this is about the UJ reaction and all the important cases in the UJ reaction. Next, let me tell you one another very hot topic. Okay, so which is similar to UJ reaction. See, here see, guys here, what we are doing is, okay, let me tell you the simple things. Okay, if the reaction is taking place between the two alkyl halides, okay, or halocycloalkanes. Okay, so in that case, okay, the reaction is called as a dry pH. Okay, then it is called as a UJ reaction, results in the formation of the higher alkane. Okay, which reaction it is? It is UJ reaction. Correct now? Okay, similar things. Suppose if the reaction is taking place between the two, okay, one alkyl halide, one aryl halide. That means aromatic halogen compound. Aromatic halogen compound. Okay, if the reaction is taking place between halide and one aryl halide, okay, one aryl halide, here loss of sodium halide. Okay, so we can see that. So what happens here? It results in the formation of alkyl aromatic compound. Everything is same. Okay, but only the thing is that alkyl halide and aromatic halogen compound. So then the reaction is called as a Wurtz-Phytic reaction. Okay, Wurtz-Phytic reaction. If you want example, you can write it like this. Okay, suppose if you take the C6H5, okay, and iodobenzene, okay, reacted with the methyl iodide in sodium in dry THF. What happens? Okay, simple. Okay, so here it forms a the toluene. Here it forms toluene. So which reaction? It is a Urji-Phytic reaction. Okay, right. And next, if the reaction is taking place between the 2 moles of aromatic halogen compounds, 2 moles of aromatic halogen compounds are taking place. Okay, so then the reaction is known as a Phytic reaction. Here, what's the product we are going to get here? We are going to get biaryl. Okay, this is called as a biaryl. So this reaction is called as a Phytic reaction. A Phytic reaction. So the name of the product is a biaryl. You can prepare a biphenyl, binaphthyl. Okay, like that. Okay, so that is called as biaryl. So these are the similar to Urji reactions. Okay, Urji reaction, Urji-Phytic reaction, and a Phytic. Similarly. Okay, let me tell you some other reactions. Take a screenshot. Right. Okay. So guys, here in the Urji reaction, what is the reagent we are using? Sodium metal. Okay, which is generating the radicals here. Okay, in DPK. So in spite of using okay the sodium, you can use a zinc metal also in dry pH. Zinc metal also. Here also you will get the same product, that is a higher alkyl. Okay, but this reaction is called as a Franklin reaction. Okay, this is called as a Franklin reaction. Okay, remember. So in the Franklin reaction, what is the difference? Only the catalyst. Okay, the difference with the Urji reaction is that only the metal. So here we are using the zinc metal, and here we are using the sodium metal. Okay, this is called as a Franklin reaction. And similarly, guys, okay, in the Phytic reaction is a Phytic reaction. So same as if you take 2 moles of aromatic iodoarenes, okay, 2 moles of iodoarenes, okay. So if you use a copper metallic copper, and if you heat it up, okay, so what happens is here also 2 moles of aryl halides involved in the reaction and results in the formation of the biaryls. Okay, but this reaction is called as a, since we are using copper, okay, this reaction is called as a Ullmann reaction. Okay, Ullmann reaction. The products are the same. Okay, the products are the same. Okay, so different catalysts are there to prepare the respective higher alkanes. So please note all these things. The similar reactions, Ullmann reaction is okay, right? Okay, guys. Well, let me tell you some other reactions. Okay, that is Core-House synthesis. Okay, let me tell you what is Core-House synthesis. Okay, here itself. Okay, simple reaction it is. Okay, Core-House synthesis. Core-House synthesis, okay, reaction what happens is, generally we will take the alkyl halide. Okay, we will take alkyl halide. And we will react this alkyl halide with a reagent, okay, that is lithium dialkyl cuprate. Okay, the reagent is, okay, lithium dialkyl cuprate. Okay, this is called as a Gilman reagents. Okay, previous competitive entrance exam question. Gilman reagent. What is the Gilman reagent? That is reagent. Okay, so that is lithium dialkyl cuprate. Okay, lithium dialkyl cuprate is called as a Gilman reagent. See, here what happens? Okay, the solvent is a dry ether. Okay, dry PHF we will use. Okay, then what happens is here nucleophilic substitution is taking place here. So how the nucleophilic substitution taking place? So guys, we know that okay, alkyl group which is present on the metal, okay, takes electrons and gets a negative charge. It acts as a nucleophile. So this nucleophile replaces halogen. So it is a nucleophilic substitution. Clear? Right. So then what happens here? We will get the respective higher alkyls. Okay, for the sake of understanding, so I am labeling this alkyl group with a prime. So here, okay, we are getting R prime. So particularly this reaction is a very useful. Okay, what is the Core-House synthesis is there? So it is a useful reaction used to synthesize. Okay, unsymmetrical higher alkanes. Okay, Urji reaction is particularly very useful to prepare the symmetrical higher alkanes, and Core-House synthesis is very useful to prepare the unsymmetrical higher alkanes. This is important. Purita, understood? Following? Okay, right. Okay, guys, good. Next, let me tell you some other reactions. Okay, so that is the very important reaction and very hot topic. Okay, about Williamson synthesis. Most important reaction. Okay, let me tell you what is Williamson synthesis. Okay, what are the exceptional and important cases are there? Okay, in the Williamson synthesis. Okay, we will discuss about Williamson synthesis in detail. Okay, so completed now. Right, good. Do you want any example for this? Okay, for Core-House synthesis, okay, you want any example? Or anything you can. Okay, suppose if you want to write the examples, okay, for Core-House take ethyl bromide, okay, ethyl bromide, okay, react this ethyl bromide with dimethyl, lithium dimethyl cuprate, lithium dimethyl cuprate. Then what's the product? How to write the product here? Okay, how to write the product? Okay, very simple now. So here which group is here? Ethyl group is here. Here take one of the alkyl groups. Which group is here? Methyl group is here. So combine the methyl and ethyl together. That's all. Okay. So you are getting C2H5 CH3 propane. You are getting, that's all. Okay, like this we can get. Clear? Right. Okay. So we can write an examples like this. Okay. So this is about the this is one of the suitable examples for the Core house synthesis. Okay. Not requires. Can we prepare the methane by the Core house synthesis? Impossible. Okay. So now let us come to the very hot topic, that is about the Williamson's ether synthesis. Okay, we have Williamson synthesis. Okay, very synthesis. For every competitive exam it is important, whether it may be for medical stream students or engineering stream students. Okay, so let's see that. Okay, what is Williamson synthesis? Okay, just a minute guys. Okay, okay, well guys, let's see Williamson synthesis here. So generally guys, what is the Williamson synthesis? As we know that, okay, the reaction which is used to prepare the ethers, okay, so by, okay, the reaction of alkoxides, okay, sodium alkoxide, okay, with the alkyl halides, okay, alkyl halides, okay, results in the formation of the respective ether. Okay, this is what we know. Correct now? Okay, right? Yes, this is right. And in which whatever the sodium alkoxide is there, so this alkoxide can act as a nucleophile. Okay, nucleophile. As we know that alkyl halides are participates in which reaction? Nucleophilic substitution reaction. So this nucleophile will replace a halogen and results in the formation of the ethers. So this is a nucleophilic substitution reaction. And this nucleophilic substitution reaction, the nucleophile attacks from the opposite side of eliminating nucleophile, that is halogen. So it follows which mechanism? So Williamson synthesis follows SN2 mechanism. Okay, it follows SN2 mechanism. Okay, and here this method is very suitable to prepare the symmetrical and asymmetrical. Symmetrical ethers and asymmetrical ethers. This is useful to prepare symmetrical and asymmetrical ethers. Okay, anything you can prepare. Okay, very useful method. Okay, so here we can prepare symmetrical or asymmetrical. Anything you can. Asymmetrical ethers. Okay, right. Okay, well. Okay, guys. So with this information, let's see. Okay, some important things. So it is following the which mechanism? SN2 mechanism. SN2 mechanism with respect to alkyl halides. So which alkyl halides will participate in the SN2 mechanism? Okay, on the how the order of reactivity, okay, of alkyl halides towards SN2 mechanism. Based on that, you can solve the many things here. Okay, very simple. So with respect to alkyl halides, okay, because in case of asymmetrical ethers are there, so then the alkyl group may be primary, secondary, tertiary. It may come from the primary alkyl halide, secondary alkyl halide, tertiary alkyl. So how it can come? Okay, what is the suitable? Okay, the combination to select these two. Okay, to understand all this, okay, just simple thing I am telling. So SN2 reactions with respect to the alkyl halide. So now let us write the order of reactivity. Okay, so that is methyl halide. Okay, primary alkyl halide is here. Okay, primary alkyl halide and secondary alkyl halides. Okay, tertiary alkyl halides are there. Okay, tertiary alkyl halides are there. So how will be the reactivity towards SN1? So methyl halides are the more reactive than primary and then secondary and then tertiary. So generally tertiary alkyl halides in this reaction, tertiary alkyl halides undergoes elimination. Okay, here undergoes elimination. Okay, remember elimination. Okay, by E2 mechanism. Okay, by E2 mechanism. It follows the E2 mechanism. Okay, now it undergoes elimination. So here you can see, okay, here also you can see that in case of the secondary alkyl halides also, here we will get a mixture of the products. Okay, here also nucleophilic substitution along with the elimination, both are possible here. Okay, so better is taking the primary alkyl halides. So primary alkyl halides are the preferred in Williamson synthesis. Okay, so most important thing, and this is acting as a nucleophile now. So nucleophilicity should be more than basicity. Okay, the nucleophilicity is more than basicity. Okay, the substitutions are the more. So which alkoxide the nucleophilicity will be more? So for tertiary alkoxide, okay, nucleophilicity is more than secondary. Okay, secondary alkoxide, then primary alkoxide. This is order of the nucleophilicity. So therefore, reactivity of SN2 will be more in this way. Okay, now easy now, most important. Right. So please, okay, write all these things, guys. I will tell you some important things about the Williamson synthesis. Okay, well, okay, let's see some other things in the Williamson synthesis. So here some limitations are there in the Williamson synthesis. Okay, so let me tell you what are the limitations in the Williamson synthesis. Okay, see, in Williamson synthesis, okay, as we know that vinyl halides, okay, CH2 double bond CHX, vinyl halide. What is this? This is vinyl halide. Vinyl halide and the aryl halides. What are the aryl halides? Aromatic halogen compounds. Okay, suppose if you take the chloro or bromo or iodo, anything you may take. Okay, take iodobenzene. Okay, or chlorobenzene, bromine, anything. Okay, just take the halobenzene. Okay, so this is halobenzene, aromatic halogen compound. Simply aromatic halogen compounds. So these two compounds. Okay, okay, cannot involve in Williamson's synthesis or esterification. Okay, na? Why? Simple. Okay, here these two compounds cannot participate. Williamson synthesis is one of the nucleophilic substitution reactions, and the nucleophilic substitution is not possible with this vinyl halide and the aryl halides. The reason is that, okay, here conjugation is there between the lone pair of electrons with the pi bond electrons. So due to the conjugation, what happens? In spite of eliminating as a nucleophile, it is forming the double bond character and coming close to the carbon. So here nucleophilic substitution is not possible. Assertion result type of questions important. Okay, now so here also same. Okay, here due to the conjugation involved in the resonance, by resonance it is forming the double bond character. Okay, in spite of taking electrons to eliminate as a nucleophile, it is forming the double bond character coming close to the carbon. Okay, and it becomes very stronger, very closer, and double bond is require the more energy to break than single bond. So that is the reason why nucleophilic substitution reactions are not possible. See, with the vinyl halides and aryl halides, since the nucleophilic substitution is not possible, and as a Williamson synthesis is a SN2, okay, reaction, Williamson synthesis, nucleophilic substitution, so which is not possible here. Clear now? Exception cases and the important the limitations of the Williamson synthesis here. Okay, put it up. So please note it. Next. So let me give you some other important reactions about the Williamson synthesis. With the different cases, I will give one more example. So with the detailed explanation, so please take it first. Okay, for example. Okay, let me tell you. Okay, so this is the case. Okay, methyl. Okay, and the ethyl groups are there. So ethyl, methyl, ether. So here let me tell you what is a suitable way to prepare this compound, combination of alkyl halide and alkoxide. Okay, that is important thing. So we have the two ways. Okay, you can break the bond here. If you break the bond here, see the oxygen is the ethyl group now, so it will come from the ethoxide. Okay, so you can write this combination. Okay, C2H5 O minus. Okay, ethoxide, and this alkyl group is there. It will come from the respective alkyl halide. Let me write a methyl chloride. So ethoxide comes from where? Ethyl alcohol. To generate the ethoxide, we have to use a strong base. Okay, strong base. What are the strong bases we can use? Okay, you can use a sodium hydride. Okay, or you can use a sodium metal directly, or you can use a sodamide. Anything you can use. Anything, any all other strong bases is a metal. So all these can produce a respective alkoxide from the alcohol. Okay, and the dry DHF. Dry DHF is compulsory. Okay, no need right here. Don't write. Okay, so these are the compulsory to use. Okay, well, so these are one of the combinations, and another combination is that if you break the bond here, what happens here? So it comes from methyl alcohol, okay, and the ethyl group comes from the respective ethyl halide, that is ethyl chloride. You may take here, okay, take the same reaction. Okay, here also you will get the same product. But what is the suitable combination for this? Okay, that is the important thing. So Williamson synthesis follows which mechanism? SN2 mechanism. In SN2 mechanism, here see what are the alkyl halides are in the competition. Methyl halide is here and the ethyl chloride is here. So which is readily participate in the SN2 reactions? Methyl halide. So this is the suitable way to prepare that compound. Here percentage of, in this way the percentage of the yield is high. Here also you will get the same product but the percentage of yield is less in this way. Okay, now following. Right. So why? Because in this way, okay, you will get the sodium methoxide. Now that sodium methoxide may basicity is more than nucleophilicity. So basicity causes to the elimination. So here there is a possibility to get the elimination product also, that is alkene, ethene. So that is the reason why. Okay, since it is a SN2 mechanism, okay, methyl halide is readily participates in the SN2 mechanism. So therefore you can take this combination to be the more percentage of the yield of the given compound. Okay, now? Okay, like this you have to select the correct choice in the Williamson synthesis. Okay, so simple logic I'm telling, SN2 mechanism. Follow the order of SN2 mechanism. Based on that, you can select the correct thing. Okay, guys, done. Well, let me tell you some other important cases in the Williamson synthesis. Take a screenshot. Okay, well, another example. Okay, that is very important example. Let me tell you that. Okay, Douglas. Okay, well, see, CH3, CH3, O, CH3. So let's see the combinations. Okay, very simple. Okay, without writing anything. Okay, directly you can write. Okay, you can choose that. So suppose if you break the bond here, okay, it will come. This alkyl group comes from the alkyl halide. Okay, it comes from the alkyl halide. It is coming from the alkoxide. Which alkyl halide? Methyl halide. That's all. Okay, methyl halides are readily participate in SN2 reaction. So the correct combination is a tertiary butyl alcohol. Okay, tertiary butyl alcohol. Okay, you can write it. Tertiary butyl. It comes from the tertiary butyl alcohol. Okay, this is coming from the methyl halide. Okay, you may take methyl iodide. Okay, in strong base like sodium hydride or sodamide or sodium metal. Okay, anything you can use. Okay, you will get this product. This is a correct combination. Suppose if you take the reverse way. Okay, if you take in the reverse way, what happens here? Okay, that is if you take the sodium or methyl alcohol, okay, sodium methoxide, okay, so sodium methoxide or methyl alcohol in sodamide, okay, directly I'm writing, and tertiary butyl, okay, tertiary butyl iodide. If you take in this way, what happens? Doctors already we discussed it. Okay, what happens here? Elimination is. Why? Because here, okay, here see, okay, alkoxide is enough. So for this alkoxide, basicity is more. Okay, here, okay, basicity is greater than, okay, nucleophilicity. Okay, basicity is greater than nucleophilicity. So if the basicity is more, okay, E2 elimination is dominating over SN2 reactions. Okay, so here nucleophilicity is more, so SN2 is dominating over, okay, E2 elimination. Okay, so based on this relation you can write. Okay, now, so here what is happening? Elimination, E2 elimination. So E2 elimination means here, okay, the reaction will take place like this. And here what we are getting here? Here we are getting isobutylene. Okay, isobutylene we are getting. So that is an important thing you guys must understand in the Williamson synthesis. Okay, this is the second case. And let me tell you some other cases also here. Okay, see how many cases are there? Easy, huh? So take a screenshot. Right, well. Okay, well guys. Okay, let me tell you some important things. Okay, about this Williamson synthesis. So in this case, okay, let me tell you, is it possible to prepare the aromatic ethers? Okay, aromatic ethers. Okay, suppose if you want to prepare, okay, this compound, what is this? What is this? Anisole, right? Very good. So this is called as anisole. So in this anisole, let's see how to prepare. So guys, we have the two ways to break. Suppose if you break this, it comes from the methoxide, it comes from the, okay, iodobenzene, halobenzene. Halobenzene cannot participate in the nucleophile substitution reaction. So this is not correct way of, okay, the bond breaking. So break the bond from here. That's all. Okay, so this phenol with the oxygen comes from the, okay, the phenyl group with the oxygen comes from the phenol, okay now, and the methyl group comes from the respective methyl halide. Okay, anything you may take halogen, okay, so other than fluorine, and here you may take the metal, sodium metal, or sodium iodide, sorry, sodium hydride, or sodamide, anything, okay, so then any solution is possible. Okay now, right, now tell me, okay, what happens here? Okay, beta naphthol, okay, reacted with the iodomethane, okay, okay, in a sodamide or sodium hydride, anything you may take, okay, all right. So what happens guys here? It can form the sodium beta naphthoxide and react with this one, and it gives up the aromatic ether. Okay, you are getting this product, right? So this is called as a nerolene. Okay, nerolene. Okay, which is used in the perfumes. Okay, is very good compound. Okay, so it is used in the perfumes here. Okay, nerolene. So to prevent aromatic ethers, we have to take the aromatic alcohols. Okay, aromatic hydroxy compound reacted with any alkyl halide, you will get the respective aromatic ethers. The reverse is not possible. Okay, now fine. And let me tell you some other important things. Clear? Okay, right. So some more reactions are there in this reaction, in this Williamson synthesis. Okay, important things to understand. Okay, suppose if this molecule is there, CH2OCH3. Okay, benzyl methyl ether. Then what is the correct way? Which is readily participate in the nucleophilic substitution reaction. Benzyles are readily participate in the SN1 reaction, then methyl halides. Why? Because, okay, sorry, the SN2 reactions, okay. So this is the SN2 now, so take the methyl halide, okay, and take this combination. Yes, this is possible. Okay, now, so you can write the correct products. Okay, anyways, okay, this is okay, hope you can write it. Okay, let me tell you some other important things, okay, that is about, suppose, see, here hydroxy group is there, and here bromine is there. Okay, so this is a compound. And write a reaction with the sodium, sodamide, NaNH2 minus. So Na plus NaH2 minus. NH2 minus will abstract this hydrogen as a proton, and it forms a respective oxide. Correct now? Okay. So can you write the product? How the product is forming here? See, that is okay. Okay, this is getting negative charge. Okay, converting into sodium alkoxide. And what is here? Bromine. Now see, within the same molecule, alkoxide is there, halogen is there. Okay, so then, okay, intramolecular nucleophilic substitution is taking place. Intramolecular nucleophilic substitution. So then see here what happens here. Consider this is the first carbon, second, okay, third, fourth, fifth carbon. So here this oxygen is going to form a bond with the sixth carbon. Okay, so let me give the numbering from oxygen because oxygen is involved in the bond formation. Okay, let me give the numbering from here. 1, 2, 3, 4, 5, 6. So oxygen is forming the bond by donating electrons to this sixth carbon. Okay, this bromine is eliminating as a bromine ion. Okay, so here, okay, 6-membered cyclic ring is going to form. Okay, 6-membered cyclic ring. Okay, just write the 6-membered cyclic ring. Okay, so in which at the first position, which atom is there? Oxygen is there. Just write it. Okay, just write it. Okay, so you are getting this compound. Okay, this is called as a cyclic ether. Cyclic ether. We are getting the cyclic ether. Okay, put it down. Easy enough. So similarly, can you prepare the THF? Okay, THF. Tetrahydrofuran. Can you suggest me a suitable way to prepare this compound? Very simple. No? So break this bond here. Okay. So this group is coming from the alcohol. This is coming from the alkyl halide. This carbon comes from the alkyl halide. Okay, just okay. Go to the retrosynthesis in the reverse way. Okay. So how many carbons are there? So 1, 2, 3, 4. 4 carbon chain. 1, 2, 3, 4. And one is attached to the bromine. Another is attached to alcohol. That's all. Okay. So now here if you react it with the sodamide or sodium hydride or sodium metal, okay, you get this compound. Put it down. Easy now. Very easy. So these are the important things to know about the Williamson synthesis or Williamson etherifications. Okay. So that's all guys. Okay, this is about the today's class, and tomorrow I am going to cover some more important number reactions. Okay, I will try to complete the number reactions tomorrow itself, and later one day I will take all the oxidation reactions in one day and all the reduction reactions in another day. Later, if possible, we can discuss some inorganic topics, important tips in the inorganic chemistry I will explain. Okay, thank you guys. Okay, I wish you all the very best without wasting your time. Okay, prepare well. Okay, prepare well. Don't compromise. Okay, with your preparation. Be healthy and prepare well. Okay, all the doctors and engineers. Okay, bye bye. Thank you for joining the class. Okay, bye.